neutral geometry. So here is a theorem of neutral geometry, which we're going to need later. And here's what this theorem says. That the sum of the angles in any triangle is less than or equal to 180 degrees. This is true in neutral geometry. And I don't know, I think this proof's actually really cool. So actually, first, let's see. First, like a little like lemma or whatever. Can you flip that over here? Just like spin that this way. Okay, first, a lemma. Sure. A lemma. The sum of any two angles in a triangle is less than 180 degrees. Prove it. Go.
You use the thingy here.
You just use the
No, not the sum.
So this is certainly true in Euclidean geometry, because the three angles add up to 180. But in neutral geometry, how do we do it? People who are mumbling, this must have something to do with the exterior angle theorem, are probably right. Should I just do this? It's kind of like boring.
Sure.
Let me just start. So take a triangle, ABC, and I would like to show that the sums of these angles, like 1, 2, 3, or whatever, the sum of any two angles is less than 180. Well, one way to do this is to just extend AC like double-sided. Call this like 4 and call this 5. Okay, so what do I know about the measure of angle 1 plus the measure of angle 2, for example?
It's less than 2 times.
Equal to 4.
Less than twice the measure of angle 4.
Less than twice the measure of angle 4. Is that helpful? Wait, I want to show that 1 plus 2 is less than 180.
Yeah.
2
That's like the
less than
exterior angle
5.
theorem gives you, right?
Which is less than 5?
Less than 2 times angle.
2 is less than 5 by the exterior angle theorem, right?
One is
Yeah.
also less than
Well, I don't even need that one. No, I don't know that 1 is less than 5, right? 5 is, an exterior angle is greater than either if it's too remote.
He said 1 is less than 4.
Well, wait, I don't even think I need that, right? If one, I know that 1 plus 2 is less than 1 plus 5. Hold on, I'm being like,
Oh,
doing
yeah.
like a math trick.
Yep.
Okay, so maybe I should write, since the measure of angle 2 is less than the measure of angle 5 by the exterior angle theorem. Right? Since 2 is less than 5, then 1 plus 2 is less than 1 plus 5. Cool, everyone see it now? And 1 plus 5
It's 180.
just is 180. And therefore, we have shown that 1 plus 2 is less than 180. Get it? Okay, wait, let's just do the other two, because why not? So it's just sort of the same thing again, right? Why is 2 plus 3 less than 180?
Because 2 plus 3 is less than 2 plus 4.
2 plus 3 is less than, no, careful, is less than, what'd you say?
3 plus 4.
3 plus 4, yeah, is less than 4 plus 3, which is 180. Why is that true? Because, I'll just put in parentheses, because 2 is less than 4. Get it? Exterior angle theorem says that 2 is less than 4, so since 2 is less than 4, then 2 plus 3 is less than 3 plus 4. Okay, last one. Why is 1 plus 3 less than 180?
1 plus 5.
Yeah, 3 is less than 5 again, right? Yeah. So since 3 is less than 5, then 1 plus 3 is less than 1 plus 5, which is 180. And so 1 plus 3 is less than 180. All right, cool? All right, so in any triangle, if you take two angles, it's definitely less than 180. All right, fact. Okay, good? Say good. Woo!
Oh, so this is the.
That was a lemma. That was a lemma. Now what I want to show now is that the entire triangle is always, in neutral geometry, it's always less than or equal to 180 degrees. Okay, so, oh boy, here we go. It's kind of like, I think I got this. Alright, take a triangle. ABC. Yeah. Alright, so start with arbitrary triangle ABC. Alright, and now what we're going to do, do you want the big picture first?
Yeah.
The big picture is that this is a proof by contradiction. So yeah, maybe I should just actually be explicit about that. So let's, I want to show that A plus B plus C is less than or equal to 180 degrees. So instead, let's suppose not. Okay? So suppose not. And of course, what is therefore the negation of the theorem we're trying to prove?
There is a triangle with greater than 180.
Yeah, so I'll just write like sum of well, okay, but I've already sort of picked a particular triangle. So the theorem, the negation would be that the sum, there's like some notation for this, I can't remember, I'm just gonna write it like this. The sum of the angles in triangle ABC is greater than 180. Cool? Okay, so how much greater? I don't know, like a little bit greater, all right? So let's let the sum of the angles in triangle ABC be equal to 180 plus like some number p. Okay, so p is the degrees that the sum of the angles in this triangle like exceeds 180. Cool? Okay, and I'm gonna we're gonna conclude this is just like impossible. All right, and the way we're gonna basically do this is we're going to say, okay, well, first of all, what's one way in which we could immediately conclude that we were done? What if P was like, 70? This is a big question.
Oh,
Then it has to.
Yeah, we know that any two angles have to be less than 180. And so if this triangle had like a 40-degree angle, am I saying that right? Yeah.
Yeah.
Then that would be like bad, right? Because if you subtract 40 from like 180 plus 70, you would get 210. That would be impossible. So actually, what kinds of triangles could we immediately conclude were impossible and like end the proof? Yeah.
Where one angle is less than p.
Where one angle is less than p, right? If you had one angle in this triangle which was less than p, then we would have a contradiction. All right, so what we now do is we produce an infinite sequence of triangles with the same, I shouldn't say infinite. We produce a sequence of triangles in which they have the same triangle sum as triangle ABC, but the smallest angle of the triangle gets smaller. All right, if you didn't actually understand any of that, it's totally fine. Let's just begin. Okay, step one. We do the following. It's very similar to the proof in the other class. Take the midpoint of BC, call this M. Cool, cool. And now extend AM past M to some point E such that AM equals ME. And connect. Okay, my claim, and this is plausible but not totally obvious, my claim is that the sum of the angles in triangle ABC equals the sum of the angles in triangle AEC. Shall we verify this claim?
Yes.
Woo! Let's do it. So I don't know. I think this is almost like overkill a little bit, but I just labeled all these little triangles. Should we do this with? Do you want numbers or do you want like pictures and colors? Okay, good. So this is like 1, call this angle 1, call this angle 3, I don't know why I did it this way, call this angle 2, 7, 5, 6, 8, 9, 4. Okay, good. So, what is the sum of the angles in triangle ABC? It's like 1739, yeah? So it's like the measure of angle 1 plus the measure of angle 7 plus the measure of angle 3 plus the measure of angle 9. But then, just like, okay, I now realize I shouldn't have listed these, I should have just used colors. Because like, what's going on here? Like 5 equals 6, of course. Yeah? And then like, what else? Because these triangles are congruent, I'm kind of, right, so, oh, I should say that. So 5 is 6 because of vertical angles. So these triangles are congruent. So what else do we have that's equal? Like 1 and 2 are equal. And also 3 and 4. So yeah. And 4. Okay, and now I think we're just kind of like a little bit done, right? Because what is the sum of the angles in triangle AEC?
2 plus 4.
So let's list them sort of intelligently. So 2 plus, there's also a 7 in the new triangle, right? Yeah. Plus, and then there is a 4, and there's a 9. But then, like, these two are equal, and these two are equal, so just like, done. Cool?
Yeah.
Okay, so, alright, so we have this sort of construction in which we have that this new triangle has the same angle sum. Okay, well, now like another sort of little mini lemma, which is like kind of obvious, which is that when we did this construction, we cut up angle A into angle 1 plus angle 7, right? Okay, so the measure of angle 1 plus the measure of angle 7, it equals the measure of angle A. Alright, now, so that's just clear, right? Now, how did we divide angle A up? Well, we divided it up into, well, either sort of evenly or unevenly, right? If we divided it evenly, then these are each half of angle A, right? If we divided it unevenly, then one of them is even smaller than half. Cool?
Main office, can I help you?
No, it's broken thingy, didn't touch.
Okay.
Didn't touch the thing.
Thanks.
Good.
Justin, I thought we
Yeah.
fixed this.
Okay, good. No, never fixed. Good. So my claim is that the measure of angle 1 is less than or equal to half the measure of angle A, or the measure of angle 7 is less than or equal to half the measure of angle A. Do you accept this claim, or would you like me to do some tedious algebra to confirm that this is true? Did you guys buy my argument from a second ago? Yeah, like it's just like a fact of numbers, that if two numbers add up to measure of angle A, and then one of them has to be less than or equal to half, right? If it's the smaller one, if they're both equal, then one of them is equal to half of A, and if they're not equal, then there's a smaller one. Okay, so what bearing does that have on my triangle? What bearing does that have on my triangle AEC? I left like one tiny inference for you to make.
It has
an angle and it's smaller. Than
Yeah, like 1 is 2, right? Yeah, 1 is 2. So if 1 and 7 are each the pieces that I divided angle A into, if at least one of them is half the measure of angle A, then that means we have a new triangle. So that means in triangle AEC, there exists an angle. So we have an angle. And I'll just write in parentheses, it's either angle 2 or it's angle 7. which is less than or equal to half the measure of angle A. And so what we have achieved here is this, what this construction does is to sort of produce a new triangle with the same triangle sum as triangle ABC, but now with an angle which is guaranteed to be smaller than angle A was. Follow? And now, and specifically not just smaller, but specifically half the size. Okay, so now what can we do?
Get there.
Keep making
Do it again. Yeah, now we do it again, and we need to be careful to pick the angle that appears smaller. Which angle appears smaller just to the naked eye here, 2 or 7? 7 appears smaller. So if 7 appears smaller, then 7 is the angle that we want to cut it into 2 pieces. So now I perform this construction of like doing this triangle, right? Do it again. But now do it on angle 7, so to speak, whereas in the original step we did it on angle A. So what does that involve? That involves taking the midpoint, and then going out, yeah, and then doing this, and now let's call this like E prime or something. So now what do I have?
Triangle with an angle less than or equal to half angle.
Yeah, right? Going through the logic again, I have, I don't know what we want to call this angle, 10 and like 11 or something like that. By a repeat of the exact same argument, I now have that, the measure of angle 10 is less than or equal to half the measure of angle 7, or the measure of angle 11 is less than or equal to half the measure of angle 7. In other words, the smallest angle in the new triangle AE prime C is guaranteed to be half, at most, the size of the smallest angle in triangle AEC. Get it? Okay, and so, do you sort of see where this is going already?
It's going to be less than B.
Yeah. So, good. So just like repeat this process, and each time you need to make a different figure based on which is the smaller angle, right? So just to sort of show what I mean, if you I don't know if this helps or not. I think this will help. So we had our original triangle, right? ABC, and we did this thing where we made E, and everything was great. And this we called 1, and this we called 2. Well, what step we do next depends on whether 1 is bigger or 2 is bigger, right? If it turns out that 1 is the smallest, right? If the measure of angle 1 is less than the measure of angle 2, then you do what we did over there, which is very bad board management. There was the E, and then we just kind of divide that, and we do it like again, yeah? Whereas, if on the other hand, if the measure of angle 2 is less than the measure of angle 1, then what do we do? Then we had triangle ABC, we did this, but now if we decide that this angle is smallest, then what?
cut AC.
Now we cut it down like that way, and yeah, something like that, okay? All right, but either way, we're guaranteed to get an angle which is getting smaller and smaller. Okay, so, yeah, how far out do we have to go? Yeah, what happens when, if we have completed the process n times. So if n times I've done this, then what can I say about the smallest angle of this new triangle? Let's give this thing a name. I don't think we can do it. If we repeat the process n times, then I started with the measure of angle A, right? So then, what is the smallest angle of this triangle? Then the smallest angle, let's call it theta n. Let theta n be the smallest angle of the triangle that results from doing this process n times. Well, the first time I did it, my smallest angle was guaranteed to be half angle A, or less. Second time, now half of that, so a fourth. So the smallest angle is guaranteed to be less than or equal to the measure of angle A, like over 2 to the n, right? Because each time I have. You guys all getting this? Am I going too slow? Maybe I'm going too slow. Okay, so how far out do I have to go? So now just like claim, eventually, this is the way like the Greeks would have done it, like eventually the measure of angle A over 2 to the n has to be less than or equal to P. Right? And at that point, what do I have?
A is less than B.
Yeah, so when eventually this is less than P, so eventually this will be true. So then what we have is that theta n is less than or equal to P. But if theta n is less than or equal to P, then that triangle, sort of like ABC, let's call it like n or something, right? This is the triangle that resulted from doing this process n times, has an angle which is less than or equal to P. What's wrong with it? What's wrong with this triangle having an angle which is less than or equal to P?
The other two angles.
Yeah, so now Bilemma on the other board, Bilemma over there, then the other two angles add up to be greater than 180, right? Or greater than or equal to 180. Yeah, I think, right? Yeah. Other two angles have measure greater than or equal to 180. I think I have like greater than sign, right? Right? Sorry, left.
Like by assumption.
What's that?
Like your left brother contradicts it.
Yeah, so
Oh yeah. Sorry, I should say. The other two angles have measure greater than or equal to 180. Bilemma, thank you. Bilemma, that is a contradiction. But of course, yeah.
Can you construct an angle of arbitrary degree in trigonometry?
That is a good question. Euclid sort of like doesn't do things metrically. If I'm using this word correctly, Euclidean geometry is like sort of synthetic is the word that they use for this, which is that you will not find any numbers really anywhere in any of the, well, in at least like in book 1, for example. He's kind of careful about that, right? So that sort of allows, so can you make an angle at arbitrary degree? The answer is definitely like not, right? The only angles that Euclid has are ones you can construct. So there's a whole sort of study of this, but just informally we can do a couple right now. Like what angles are constructible in Euclidean geometry? Well, what do we know how to do? We know how to make right angles.
bisect.
We know how to bisect right angles. So I can get 45, so to speak, half of that. So any like 180 over 2 to the n, those angles are all constructible. I can also make equilateral triangles. So that's, I get 30. So I can also get half of that, etc., etc., etc. And what you basically get is this kind of world in which like some angles are constructible. These are referred to as the constructible angles. But then some like aren't. Like I can't remember, Kevin, you know what's the first one that you like can't make? Like you can construct an angle of a pentagon. So it's like something like, I think it's like the 23-gon or something like that. Finding like you can't construct a 23-gon. That might be the first polygon, the first regular polygon that's just simply not constructible. More on this later. This is going to come up later in the class. I should know these things by heart, but I don't.
My question was more just like, what if you drew an angle and said that it was measured P, and then you drew an angle inside of that so that it was guaranteed to be less than P because the part is less than the whole, and then you drew a triangle inside that angle. then you would just have a triangle with a degree that's less than p, or with an angle that's less than
But it's
Right,
not about,
but-
it's about taking an arbitrary triangle with the only thing you
Yeah.
know about it is that it has greater than 180
Oh,
degrees.
oh,
and
yeah,
then
my bad.
prove
That's right.
that it's
Yeah, wait.
impossible.
The logic here is very subtle, and I've been very casual about this for whatever reason. I don't know why. Because you guys look kind of bored, so I went faster. Or I thought I was going faster at least. So let me just repeat the logic. It goes like this. But Anson's exactly right. Take arbitrary triangle ABC, any old triangle whatsoever. What I'm trying to show is that this triangle, it must be the case in this triangle that the sum of all three angles is less than or equal to 180. Proof goes like this. Suppose not. Well then, the sum of A, B, and C must be more than 180. Let P be the amount by which it exceeds 180. Now, via this ingenious construction, I make an entire family of triangles, each of which, by construction, have the exact same triangle sum as triangle ABC. And the contradiction arises, I wasn't totally explicit here, but I thought it was good enough. The contradiction arises because I have produced a triangle, triangle ABCN, the result of performing this operation n times, which, by the construction, has the same triangle sum as ABC. And yet, it has an angle which is less than or equal to p. And so, if you take that out, then the other two angles must add up to be greater than 180, which is a contradiction to the whole construction. Follow? Okay, this is interesting because, yeah. So basically in neutral geometry, this is already starting to give us kind of like a sense of what neutral geometry like sort of looks like, so to speak. You have like less than or equal to 180 degrees in every triangle. And if you have exactly 180 degrees in any triangle, or if you even have a single triangle with 180 degrees in it, then you're in Euclidean geometry. All right, cool. All right, was that fun? You guys no one looked like they were having fun. Okay, bye, period. I'm sorry you have to watch this depressing video. Good.